go. So to start off our review for today, if you're given a complex number and you're asked to find the argument of it, recall that the argument is just whatever your theta is, and we calculate our theta by doing the tan inverse of b divided by a. All right. Now, in the past, we were practicing on trying to find the unit vector, seeing where it falls on the unit circle, and then calculating our answer. I want to say it was in this class or last class or the next class that asked, couldn't we just use this formula every time and it would give us the answer? The answer is yes. So instead of spending so much time on finding that unit vector, if it doesn't tell us to find it, then let's go ahead and just use the equation given. All right, so in this situation, this would be the tan inverse of what? 1 over 1. One thing I want you to note is if there's not a number next to your I, there's an imaginary 1. Another thing I want to note, if there's not an I at all, what is your B? 0. If there's not a real number at all, what is your B? A? 0. Okay, so just make sure we have that clarification there. All right, when you type in the tan inverse of 1 over 1, what do you get as your answer? Okay, yes, you do get tan inverse of just 1. All right, and then when you do that, what do you get? 45 degrees. One thing I want you to make sure you pay attention to is what quadrant did 1 plus I fall in? Quadrant 1, right? It fell right here. Do I have to do anything to that degree? No, so 45 degrees is my answer. Now, also, if we would have found the unit vector, we would have had to find the modulus, divide it by the coordinate, and you would have found out that you would have ended up on the square root of 2 over 2, comma square root of 2 over 2, which will then told you 45 degrees. But that would have been another 5 minutes of work. So again, I think this is a easier and better way of always doing it, unless the directions specifically say, hey, what's the unit vector? All right, so we got our argument. The next question is asking for these absolute values. Please, at this point, tell me y'all know what these absolute values mean.
Yes.
The distance. You have the square root of a squared plus b squared. These absolute values have many names. This is the modulus. This is the r. This is the distance. This is magnitude. Yes, thank you. And that all equals the same thing as the square root of a squared plus b squared if you're finding the distance from the origin. If you happen to be looking for the distance from 2 points, remember our equation changes slightly and becomes the difference of the x's squared plus the difference of the y squared. I was talking to Mr. Whiting the other day, and he says the way he teaches y'all is he has y'all move y'all's vectors back to the origin and then go right back to this a squared plus b squared. That concept works, but that's also, in my opinion, a lot of work to just move something when we could just find the distance using the formula. All right, but both ways will work. All right, so then we come over here and we do the square root of 1 squared plus 1 squared. And what's 1 squared? All right, and then 1 plus 1 is square root of 2. All right, can I do anything with the square root of 2? No, leave it like that. I do not want a decimal. The quiz is not going to want a decimal. It's going to have a little math function keyboard for you, so you'll be able to hit the square root and type your numbers in and arrow out, just like as if it was a calculator. So the square root of 2 would be the answer that it's looking for. Questions on that? What if this was the square root of 8? Right? What would it have to do with the square root of 8? Good. You need to do your little factor tree. So what two things multiply to 8? And then what multiplies to 4? How many numbers do I need to pull out? 2 of them. And then it pulls out as one single of that. Any hanging tree limb that's still left would stay inside the square root. Again, this would be the answer that the program's going to want, not this one and not the decimal. So be able to do this. Now, I'm not saying this is the answer to this one. This is just a different example. Correct. It might give you partial credit for not simplifying, but I do not know if the program will give you partial credit. Questions? All right, so that's the beginning there. So let's look at some exploratory challenges, which basically the stuff that we've already kind of done. All right, without actually graphing this, you should be able to look at this and tell me the geometric effect. Now, this is exactly what your quiz was asking you on Tuesday on question 1. What effect does 1 plus I have on any vector or not any complex number z? And how would I figure this out? Z is any complex number. So technically, z doesn't matter. What you're asked is, what does 1 plus I have an effect on any complex number that happens to be z? So when you're given this question, especially on that quiz on Tuesday, the z doesn't really matter. All your stuff here is right. Yeah, that part's not going to affect it. This is going to affect the z. So there's two things that multiplying by a complex number did. What were those two things? Well, it dilated and rotated. All right. You technically just did the math in the opening exercise. What was the degree of rotation? 45 degrees. So that's what I expect to see. Degree of rotation. You did it in the opening exercise. You got to find the argument of 1 plus I guess technically doesn't have a name. Right. And we did that in the previous example. The argument was a degree of rotation of 45 degrees. Counterclockwise, whoever. Yes, perfect. Counterclockwise. Are we hot, cold, or are we content? All right, hot. You changing your vote there in the middle of it? Neutral. Okay, so 4. All right, content. Ooh, that's 4 to 4. 5. Okay, so we're content. Sorry. All right, sorry about that. I got hot. Now this is one. All right, so that's the first thing you do, and then you need to figure out your dilation. To figure out your dilation, you would want to figure out what the modulus is of that complex number, which we did in part A. We calculated it as the square root of 2. So you would say, was it a dilation of a scale factor of square root of 2? Good. Note it, but stars around this now because you're going to get to use this. And I try to condense all of 9 through 17. I say I did, this book did, but all in one spot. Any questions on that? All right, so I want you, well, actually, let's go into this. So that's the geometric effect. What's being asked now is we want to undo this 1 plus I. So you're going to basically think of what is the opposite of this. So if you went 45 degrees counterclockwise, what would I have to do to undo it? Clockwise, right? So that would be in a sense of going 45 degrees clockwise instead of counterclockwise. Or you could say negative 45 degrees. Right? Either one would work for me. And then if I dilate it by a square root of 2, what would I have to do to undilate it? Not negative. When I dilate something, I'm doing what to the complex number? What operation? I'm multiplying it. That's what makes it bigger or smaller. So if I'm multiplying my complex number by a square root of 2 to make it larger, what would I have to do to, I would need to divide it. Now, how would you write? So you really can't say divide by square root of 2. What would I have to multiply in order to divide by the square root of 2? If I asked you to divide by 2, that's the same thing as multiplying by what? Not 1. All right, let's ask this question. Okay, 0.5, which is a half, right? So if I asked you to do 4 divided by 2, that's the same thing as 4 times a half, which is 1/2. So if that same philosophy, if you're multiplying by the square root of 2, what could I multiply by to divide by the square root of 2? How would that fraction look like? If I had this, not 0.5. 1 what? Not 1/2. Not 1/4. What am I multiplying by? Yeah, you do. We just figured out the dilation, the square root of 2. So if I want to divide by the square root of 2, 2 over 2. No. What is it? I heard it. 1 over the square root of 2. So I would have to multiply by 1 over the square root of 2, which is the same thing as dividing by the square root of 2. Why? Because, again, 4 divided by 2 is 2, but so is 4 times 1/2. I can't divide by a scale factor. I can only multiply. So if I want to divide by the square root of 2, I can multiply by 1 over the square root of 2. All right. So that's how we can undo it if we were asked to do that. Right. So like for instance, let's say I did this. Let's say hypothetically, this isn't part of the work. Let's say my z equaled 2 plus 3i, right? So if I know that and I multiplied by the square root of 2, I would get 2 square roots of 2 plus 3 square roots of 2i, because I would multiply by a scale factor of 2. But if I want to undo that, I could multiply this by 1 over the square root of 2. And we know that we're multiplying fractions straight across. So both of these would go over 1. And then this would become 2 square roots of 2 over square roots of 2 plus 3 square roots of 2 over square roots of 2i. What's going to happen to those square roots of 2? They cancel each other out, going right back to my original vector or complex number. Right? This is just side work, has nothing to do with the actual stuff. Right? So side. It's an explanation on why we're multiplying by 1 over square root of 2. Okay. So basically what you did is you just found its inverse. Right? So whatever the inverse of the scalar factor is what you're going to end up multiplying by. Remember, inverse means just flip the fraction. Right? We all good with this so far? All right. All right, let's move on to 3 then. All right, so now that you're in this example, it says, given that the argument of z will be between 0 and 2 pi, which just basically means it's somewhere on a circle, for any complex number, how could you describe any clockwise rotation of theta as an argument of a complex number? What this is basically stating, if you are looking for the argument of z, and you know it falls somewhere on the circle, and you know you're have a clockwise rotation. So basically it told you what the undo part is. All you have to do is take 2 pi minus whatever that clockwork notation is. So for instance, if I went 45 degrees clockwise, right? That's like a negative 45 degrees. So then that would be, let's think about this in degrees as well. You don't. You're just forming an equation. Right, so we have a radiant one and we have a degree one. What this is basically stating is, if you know that clockwise I went 45 degrees, then I would take 360 and subtract 45 from it, and that puts me where? 315, which is the same concept as a negative 45 degrees, which we know goes clockwise. That's all this formula is telling you. So if you're given the degrees in clockwise rotation, which is what it's stating here, then all you got to do is take whatever this is and subtract it from 360, and you'll get your counterclockwise answer, which is what all of our degree of rotations are. You don't know. I'm just saying, if you knew what theta was, you're not solving anything. This is your equations. This is just stating, if I told you this guy rotated 90 degrees clockwise, and I wanted to find out what the degree of rotation is, because that's what the argument is, and it's a counterclockwise motion. It's not clockwise motion. I would have to take 360 minus 90, which is what? 270, which would then fall here. Right? So this would be your degree of rotation, because it has to be counterclockwise, as Elijah pointed out in the opening exercise. or number one, actually, number one. And that's all this is stating. So on the quiz, it could tell you, hey, what is the degree of rotation if it rotated this way clockwise? And you just subtract it from 360. Now you have your answer. That's all this is stating.
Whenever we get that answer,
It depends on what it wants. So if it was in radians, let's hypothetically say it turned pi fourths clockwise, you would take 2 pi minus pi fourths. If you're really bad with fractions, just do 2 minus 1/4. It'll pop back out as in 7 pi fourths, and 7 pi fourths happens to fall right here, which is still negative pi fourths, which is clockwise direction. Right? It just depends on what the question's asking. Then. If it's asking for you to radians, you subtract from 2 pi. If you're asking degree, you subtract from 360. Any other questions like that? So this is just formulas, no actual math. This formula is given in the situation that you might be told the clockwise rotation and you need the counterclockwise answer. Go ahead. It won't, because it has to fall between 0 and 2 pi. Because remember, I can go infinitely many times, but I'm still going to land somewhere on that circle. Yeah, it'll work every time. All right. So in part 4, or example 4 here, it says write a complex number in polar form that describes the rotation and dilation that will undo the 1 plus I, right? So in our situation, we were given the argument of this random, we'll call it W, because I don't know what else to call it. We found out that we had to go negative 45 degrees clockwise to undo this, correct? Okay. But if it's negative 45 degrees clockwise, what would be its counterclockwise? So if you're given the clockwise, which we were told in number 2, we calculated that it needs to go 45 degrees clockwise. Right? So you were given that, you figured that out. So to figure out its counterclockwise, what do? Subtract it from 360. So what's 360 minus 45? Number 3 is just an equation. Number 4 is an actual example. All right, so do we all see how we got 315 degrees? So we figured out what needed to be done to undo the 1 plus I. It needed to go 45 degrees clockwise since it originally went 45 degrees counterclockwise. Well, 45 degrees clockwise means 360 minus 45, which gives me 315 counterclockwise. We still good with this? All right. Then you calculate it. And again, I'm just randomly calling this vector W, or this complex number W. But what was the modulus that you calculated to figure this out? What was the inverse part? Bless you, on number 2. 1 over square root of 2. That was the modulus that you needed to multiply to undo the original modulus. So what it's asking for is, well, can you give this to me in polar form? Recall, polar form is cosine. Oh, I lied. Is R times cosine theta plus I sine theta. Right? So all we're going to do is just plug it in. R represents what? Not the radian. The modulus. All right. So even though I wrote the square root part, or the absolute values, this ends up being 1 over the square root of 2 times cosine of what was my argument? 315, because I need to go counterclockwise, plus I sine of 315. All right, so we turn this into polar form, and then it wants us to then convert it into rectangular form. So in the next step, I'm going to do that. So I'm going to have 1 square root of 2. I now need to use my unit circle. I would go to 315 degrees, and what's the coordinate for cosine and sine? Right, what's the coordinate though? So this becomes a minus square root of 2 over 2i. All right, this is where I'm at so far. Anyone lost? So this came from number 2 that we talked about. I plugged it into my polar form, so don't forget this guy. And then I used my unit circle to get my coordinate. Now what do I do after this? I multiply. All right. And when I multiply fractions, how do I multiply fractions? Straight across. All right. So I'm running out of room. So this ends up being 1 times square root of 2, which is square root of 2. And then this ends up being square root of 2 times 2, which is square root of 2. Sorry, 2 square roots of 2. I cannot multiply these two numbers. One's in a radical, one is not. And then minus, what's 1 times square root of 2? Square root of 2. And square root of 2 times 2 is perfect. What can you see happens? The square root of 2's can cancel. So my final answer up here, I'm running out of room there, is what number is left on top though? Not 0. There's always a 1 as a placeholder. And think of it like this. What's 2 divided by 2? 1. So there's always that 1 left over. All right, so this is 1 over 2 minus 1 over 2i. There is your complex number that you could multiply to undo your original complex number that you multiplied at the beginning on the opening exercise. Gosh, man, I'm trying to remember things. It was. Sometimes my brain's still foggy. All right. Yes, ma'am. All right. As always, there's an easier way to do this, right? Let's talk about the easier way. So in a previous lesson, we learned to undo 1 plus I, we can just multiply by the reciprocal or the reciprocal inverse, right? I think that was in lesson 9 or 10 or something like that. Or I think actually lesson 8. No, I think it was 9. Sorry. All right. So we're going to write the complex number 1 over 1 plus I, and we're going to put it in rectangular form. So check this out. In the very beginning of this process, you were asked to find out what 1 plus I to the z was. You calculated that it was a 45 degrees counterclockwise and had a modulus of the square root of 2. That's what we did in open exercise and question 1. On question 2, you then had to undo it so that we thought backwards. We're like, all right, to undo a 45 degrees counterclockwise, let's go 45 degrees clockwise, which is the same thing as 315 degrees counterclockwise. And to undo the modulus, instead of multiplying by the square root of 2, we multiplied by 1 over the square root of 2. We then had to plug all that into polar form, condense it down to rectangular form. Seems like a lot of work, right? Watch what happens when I take what I'm multiplying and I just figure out what its inverse is and see if we get the same results. So the inverse of something is basically put it under 1. Right? We learned this in, I'm pretty sure it was lesson 9, somewhere in that area. All right, so I'm going to do 1 plus 1 plus I. But when we did this, we were told that we can't have an I on the bottom of a fraction. So what do I had to multiply by to get rid of that I on the bottom? The conjugate. So what is the conjugate of 1 plus I? Put in a 1 under it. Yeah, but under 1. We know on top, 1 times this is just going to be 1 minus I. And then on bottom, we talked about how to multiply conjugates, right? It's the FOIL, but it's really just the F and the L part, which ended up just being A squared plus B squared. So what I'm going to do here is I'm just going to do the F part and the L part, which is again A squared plus B squared. What's 1 times 1? 1. What is I times negative I? Negative I squared. Negative I squared turns into a what? A positive 1. What's 1 plus 1? how would I rewrite this as a complex number? Is that the same answer we just got on number 4? Yes. So here's the thing: if you are asked to find the what undoes a transformation, just find its inverse, right? Which is 1 over whatever that complex number is, and then put it back in its correct form, and you get the same answer without having to put it in polar form, figuring out on the unit circle, and then working it down back to rectangular form. Which way seems easier? This one, right? So we're asked to transfer. If you're asked to undo a transformation, so undo a transformation, just find its inverse. And to find the inverse, we just put a 1 over under it, or put it under 1. All right, number 6 is basically, did you notice that 4 and 5 gave you the same answer? I'm just going to put a big old yes here. Hopefully you did notice that. I'm not going to go into much detail there. Questions there, though? All right, so both ways do give you the same answer. This is a lot easier of a way. Skip 7, go ahead and cross 7 out. I want to focus on 8. This one says, show that the statement, when z equals this, the reciprocal of complex number z with modulus r, an argument of theta, given these things here, give you the same answers. Right? So what we're going to do is we're going to figure out what we just did at the same time to see that both answers are the same. So here we go. So first thing we need to do is we need to calculate the, I guess the modulus is probably easier. What's the modulus of this, and how would I find it? A squared plus b squared. So this would be 2 squared plus z. Yeah. It's not complex. How do I know if something's complex? Yes. Two dots. Oh, that's like a semicolon. That's like saying, hey, show that the following is true when this equals this, given the reciprocal, and then it just tells you what the reciprocal of all these things are. Yeah. So this is like, hey, use this to prove that this is true. I got you. Yeah, no, those 2 dots have nothing to do with the actual complex number. This is a semicolon, like when you list something in English. All right, and then I go and I do my b, which is 2 square roots of 3 squared. Did y'all notice I didn't put a negative here? Is it going to matter if I don't put a negative? No, it's not, right? All right, so let's work this out. 2 squared is 4. When I have a coefficient and a radical, what do I need to do with the square? I got to square both of them. All right, so what is 2 squared? Very good. And what's the square root of 3 squared? 3. So then I have to multiply that result. So what is 4 times 3? So what's 4 plus 12? What's the square root of 16? 4. So we got a modulus of straight up 4. Okay. We all good on that? Now we got to find the argument. How do I find the argument? Tan inverse of b over a. What's my b? Negative. This is going to matter on the negative or not. So definitely make sure if it has a negative that you apply. So I get negative 2 squared root of 3 over 2. When you type that in the calculator, what do you get? Negative 60. All right, now the issue comes, what quadrant does that fall under? Yes, you're right. Yes, sorry. I was thinking it was 2. So it does. It falls right over here in quadrant 4. So what does that mean? What do I have to do to this degree if it falls in quadrant 4? Add 360 to it. So what's negative 60 plus 360? 300. So there's your argument. All right. Now, what it's asking, now that you've figured out the modulus and you figured out the radiant, or not the radiant, the argument, it wants to prove that what we did earlier gives us the same thing. So earlier, I had to figure out what the inverse of 1 or 4 is. What's the inverse of 4? So that's 1 over 4 times the cosine, because we're going to go with the polar form. The theta, though, that's going to be 2. Well, in this case, we'll do 360 minus theta. So therefore, what is 360 minus 300? 60. So that'd be cosine of 60 plus I sine of 60. Oh, because we're doing the reciprocal of it. That's what it's asking us to prove, that the reciprocal of these is going to give us the same answer. So the reciprocal of the modulus was 1/4, and the reciprocal of the argument would be 2 pi or 360 minus theta. Yes, sir. The reciprocal of 4 is 1/4. Reciprocal means flip the fraction. So if you get they mean the same thing. Reciprocal and inverse is the same thing. Reciprocal equals inverse. Good question. All right. What is the cosine at 60 degrees? And then what would I do here? Multiply. So what's 1/4 times 1/2? 1 over 8. Because again, you just multiply straight across. What's 1/4 times the square root of 3 over 2? Perfect. All right, so there's your answer. All right, now what it's asking is, does our process still work? Could I just figure out what the inverse of this guy is? And remember, to find the inverse of this, it's going to be 1 over 2 minus 2 square roots of 3i. What would I then have to do? The one in the middle, right? The imaginary number sign, right? So this becomes what? Perfect. What I do to the top or the bottom, I have to do to the top. So again, what we're doing is this is the way we saw on 1 through 4. This is what we saw on 5. We're just proving that they equal the same thing. All right. So what, or checking that it gives us the same thing. It wasn't just a coinkydink, right? That's a 3i. That looks horrible. That's a 3. All right. This right here is just going to be the same thing. So 2 plus 2 square roots of 3i. And again, when you're multiplying by the conjugate, all you have to do is just do the F and the L part of FOIL. So what is 2 times 2? 4. And what's negative square root of 3i times 2 square roots of 3i? Let's break it down. What's negative 2 times 2? And what's the square root of 3 times the square root of 3? 3. And what's I times I? I squared, right? Negative 3 times 4 does give us what? Negative 12. So this becomes negative 12i squared. And then that I squared is going to make that a what? Positive 12. So I now get 2 plus 2 square roots of 3i over what's 4 plus 12? 16. But I want to write this as a complex number. So I want to separate this as 216 plus 2 square roots of 3 over 16i. What does 2 over 16 simplify down to? 1/8. And again, same concept, but I don't necessarily need that 1 in this case because there's a square root of 3. That's an 18. Did I get the same answer? So again, both of these processes are the same. It just depends on what you think is easier. I feel that the green is easier, but it might be that the orange is easier for you. Either way works for me. Yep, I did it by parts. I did the numbers outside the radical. So I did -2 times 2, and that gave me -4. Then I did the radical itself. The square root of 3 times the square root of 3 is what? Square root of 9, because you're multiplying. So 3 times 3 is? Square root of 9 is 3. So that just comes down to 3. And then I did my i's next. So then I times I gave me I squared. So now that I have it all written here, I then put it all together. -4 times 3 gave me -12. And then I now know that I squared is going to change this 12, +12. So this really ends up being just 4 plus 12, which was 16. You can cross out number 9. We're not going to do number 9. Any questions on this? So if you're asked to find something to undo your transformation, you can either do the inverse, or you can go through this process of taking the reciprocal of both the modulus and then the argument. But to find the reciprocal of the argument is 360 minus theta or 2 pi minus theta, depending on what you're dealing with, and then putting it into polar form, working it down to rectangular form. All right. Either way works. Okay. Any questions? So that was the last thing that's going to be new. Now, if you go on to, I don't know what page, number 10, this is going to break down everything from lesson 9 on. All right. So let's go through that. I don't know what they call it. An infographic organizer or something. Is that what that's called? It has like all your information on an organizer with graphs. I don't know. All right, but that's what this is. All right. So in lesson 9, the first thing we learned was how to add complex numbers. We did z plus w, right? And what did we learn that affected the graph? For instance, if I added a real part, what did it do to the graph? It shifted what direction? Not real, left and right. Remember, the real axis is the x-axis. So when I added or subtracted something, it moved that complex number left or right. So if I add a real, it shifts. If it's positive, it'll be right. And if it's negative, it'd be left. And however organization you want to put that in. If I added a imaginary, it shifted what? Up and down. So if it was positive, I shifted up. If it was negative, I shifted down. So that's what we learned in lesson 9. Okay. Over here, it's just giving an example so you can remember that. So here we go to verify. 3 minus 3i plus -2i, right? Let's do the math. So how do I do this? When I'm adding, what do I do? Yeah, I know this. Combine like terms. So what's -3i plus -2i? Perfect. No, when you're adding, you just add the coefficients. When you multiply, that's when it becomes a square. All right, so there's your answer. Now, without doing the work, could you also tell me what the description is of what that -2i did? There you go. Shift down 2 units. All right. This is a comma. Shift, before, plus. Sorry, I'll be more clear next time. All right, just to kind of verify it real quick, 3 comma -3, that's 1, 2, 3, 1, 2, 3 is like right here. And then 3 minus 5i would just mean I go 1, 2, and I shift it down. So you can physically see that it shifted down 2. We all recall unit or lesson 9. All right, in lesson 10, we talked about subtraction, right? So we said, all right, what happens if I subtract these two? Well, it's going to do the same effect. So if you want to recopy this in, so I guess really what I should have wrote here is right and up, and then this would be left and down, but same concept. All right, so you can rewrite it here when you're adding and subtracting. So if I have 3 minus 3i minus negative 2i, what's going to happen to these two negatives? Make it a positive. So when I combine like terms, what do I get? -1. All right, we could call it -1i. I wouldn't count off for that. The negative I is kind of what your answer. So if this is a multiple choice question, that's what you're going to see. And can you describe what happened here? It went up 2 this time. So shift up 2 units. So even though it was subtracting, because it turned it into a positive, it did the opposite of what the sign was, which in this case is shift up. If you don't believe me, you can always graph it. So 1, 2, 3, 1, 2, 3. This time 3, -1 would put me right here. So I can see that I shifted up as this one shifted down. Okay. Any questions on lesson 9 and 10? All right, let's go on to lesson 11. Does everyone have this before I erase it? Okay. All right. In lesson 11, we start really heavily talking about the conjugate. So what's the conjugate of, what was Z? Actually, okay, let's just talk about what the conjugate did graphically. What did the conjugate do graphically? We talked about this yesterday too. Reflects across what? The x-axis, because what sign does it change? Which is what part? The imaginary. So it changed that y value to a positive or a negative. So it goes up or down. So this is a reflection across the x-axis. What is the conjugate? Don't forget that the conjugate is just the line over. That's the notation there. So what's the conjugate here? For z, on the very top. Good. In this case, it'd be 3 plus 3i. To give you a graphical part of it, 1, 2, 3, 1, 2, 3. This is where my original z was. 3, comma 3 would be 1, 2, 3. Will be now here. So you can definitely see it was a reflection over the x-axis. We go with lesson 11. Right? Let's move on to lesson 12. Lesson 12, we talked about what effects the multiplication had on a complex number. All right. When we were multiplying, there was a couple of things. When we multiply by a real number, what effect did it have? Yes, it dilated. All right. But it dilated by what? How do I find out my dilation? Gentlemen, are y'all got this all down pretty good? It's pretty easy. All right. Oh, I was concerned about the two I had lined up there with their head down. All right. But how do I find out what that dilation is? What is it? Dilated what? What is it that tells me the dilation? No, we don't know it, but in general, what is the dilation? How do we find it? It does. It gets bigger and smaller. Yes. Multiplied by the what? Modulus. Right. So you're going to dilate it by whatever the modulus is. Right. Whatever that is. If I multiply by an imaginary number, what effect did that have on the graph? Braden, go ahead and put it up. It was a rotation. And how did I calculate this rotation? Okay, that's the imaginary part, but how do I calculate it? What is it? A rotation of what? In general, how do I find it? The rotation. How do I find the degree of rotation? Huh? The theta. Very good. Of the theta. right? A couple of things I also want to add in here. How do you find the modulus? What's the equation? Not modulus, modulus. Square root. Now, how do you find the degree of rotation for the theta? Perfect. All right. So this was all in lesson 12. All right. So to work this out, let's find out what this W had on the effect. Now, notice I'm trying to find the effect of W since it came first. All right. So I calculate my modulus for W by doing the square root. What's my A for W? Braden. Put it up. Huh? All right. So what is it? What's my A for W? Nothing, right? So that's going to be 0 squared plus what is my B? -2. Don't stress about it if you forget the negative. 0 squared is just 0, and then -2 squared is 4. So what's the square root of 4? 2. And then to find the argument of W, remember it's tan inverse of B divided by A. But what's my B? Ooh, I like this. B divided by A, yeah. Nothing. Can you do that? Check it in your calculator. I'm curious. 0 on the bottom can't happen. It does say undefined in the calculator. That's so interesting. All right. So when this happens, there is a rotation, but we're going to have to divide the modulus by our coordinate. So this actually does not work all the time. That's fascinating to know. All right. So when you get 0 on the bottom, we have to use our unit vector idea. So what's the coordinate of W? What's the coordinate? So it'd be 0, -2. And then if you recall, to find the unit vector, I took my vector or my coordinate and I divide it by the modulus. So what's 0 divided by 2? 0, and -2 divided by 2? -1. Which then puts me where? We got the 270 degrees. I did not realize that was us. I want to practice more. I think I'm going to push the quiz to tomorrow, to next week. I want to keep reviewing because we only made it to lesson 12. I think so too. I like this graphic organizer they put in here.